No, question 12. Do I have these here? I do. I think I do. This is um, on rigid body. Okay. Okay. Yes, I remember this one. It's so tell me if this isn't it. But so I think this is one with, okay, and then you have, yeah, gears. Okay, and it tells you what coordinate system to use. The y-axis goes that way. The x-axis goes this way. And the z-axis comes out that way. Um, and you have a 96-pound force there, a 265-pound force there, 192 pounds there, 530 pounds. The gear on the left, so this one has a radius of 1.5 inches. And the one on the right has a radius of 1/2 inch. Calculate the reactions. Oh, and we need some distances. Uh, so this distance is 4 inches, 3 inches here, even though it looks longer. Okay, there's a middle one. Okay, it doesn't look longer. This is 3 inches, and this is 2 inches. So 3 here, 2 here. And we want to calculate those reactions. Well, we're going to isolate the, so we'll isolate the shaft and the 2 gears as a single thing. And then the reactions with those two supports, we're just going to represent as loads. So let's see. There's that. Thanks. Okay, and then there are no masses. So what kind of loads are these? Well, here's the easy stuff. There's that force there of 96, that force there of 265, 192, and 530. And now at the two pin joints, what are the reactions there? It doesn't say anything about whether those pin joints provide thrust or not. Sometimes a picture might show you something that would indicate whether it provides thrust, but there's nothing like that in this case. You can't see any little flanges there or anything. So let's first start by assuming that those pin joints don't provide any thrust. And then we'll start looking at equations and stuff like that, see if it's possible to calculate it that way. So if you're dealing with pin joints in 3D, the first thing you have to think about is whether they provide thrust. The second thing you have to think about is whether they provide those couples. What do you think about those couples? Are those going to be in there in this case? They're not. And why is that? That's right. Those two share the same axis, and whenever that happens, you don't have to deal with those individual couples provided by, the couples provided by the individual things. So the forces provided here are, try to make this sort of obvious what axes I'm talking about. Over here they call this C. I'm going to call this, there's a force RC in the Z direction and a force RCY. The x-axis is along the axis of rotation, so for now we're not going to assume there's any thrust. And then at D, same thing, there's going to be a force component RDZ and a component RDY. And now we've dealt with all the reactions. We're not given any weights or anything, so this is it. That's a complete free body diagram. Let's choose the about point. I suppose over here is as good a place as any. And I'm going to set it up with rho, force, moment. Okay, so I'll start with that force RC. That's at the about point, so there's no rho vector. The force vector is, we don't have any x components, so that's 0, RCY, RCZ. I'm doing it as two components of a vector, but you could also do those as two individual force vectors, and they each have their own rho. It would come out just the same. And there's no moment. And then there are two forces applied at the top of the big gear. So, I don't know, big gear. So the force vector, the vector from the about point to where those, and I'm going to write that as a single force vector because it's at a single point. The vector from the about point to where that force vector is applied is 4 inches in the positive x direction, and then 1.5 inches in the positive y direction. So 4, 1.5, and then 0z. And the force vector, we have 96 in the negative y direction, nothing in the x. Negative 96 for y, and then positive 265 for z. Can someone calculate that with a calculator, that cross product? I guess I don't care if you use a calculator. You can use an abacus or something if you want. Do you like abacuses nowadays do cross products? Has abacus technology improved? Okay, maybe a calculator would be better. I don't know. I like to think there's just really cool abacuses now. Yeah. The TI 97 abacus. Oh yeah, that's true. Yeah, that is a good calculator name. What is it? 0x? Oh, 397.5. Negative 1060. 384. Okay. And then we get to RD. And that is at just 7 inches from the about point in the positive x direction. So 700. And that is 0x RDY RDZ. And the cross product there is 0x negative 7 RDZ and positive 7 RDY. And then at the small gear, actually, now that you say that, I think there is like some kind of graphing program or something called Abacus. There, yeah, seems pretty obvious. Yeah, exactly. Um, so that location is positive 9 in the x direction, and then 0.5 in the positive z direction. So 9, 0, 0.5. And the force vector is 0x, 530y, negative 192z. And can someone calculate that cross product? I'll start. Negative 265. Anyone? Okay. Okay. All right. So that's it. And now we're going to Newton's laws, and we're going to see some stuff here that we haven't seen in other problems. We're going to have to, just sort of make sense out of it. So Newton's second law says 0 RCY RCZ plus 0 negative 96 265 plus 0 RDY RDZ plus 0 530 negative 192 is equal to zeros. We can see it didn't matter that neither of these joints applied any thrust, which I guess we could have just seen from the free body diagram. You can see no forces are acting in the x direction. So this will all go away. We can forget about the x force equation. We've done that before. And now the moment equation says 0, 0, 0 plus 397.5 negative 1060 negative 384 plus 0 negative 7 RDZ 7 RDY plus negative 265 1728 4770 is equal to zeros. And here's the thing we haven't seen before. This equation is not possible. Yes. No, because the y component of the cross product is always a little, that you do that and then you multiply the whole thing by a -1. So what we get here is that this thing along the x-axis is not static. Okay, so let's say rotation about the x-axis isn't static. You know, there has to be some kind of angular acceleration there. As long as this is starting from rest, that doesn't matter because we're not trying to calculate any couples about the y-axis. So as long as it doesn't already have, when we're doing this calculation, some angular velocity, we can still do this. Things get weirder if you have angular velocity. Because there's no reaction moments about the x-axis. Okay, so that means that we'll just forget about this. And now we have 4 equations left. And we have 4 variables. And that means we can solve it. Any other questions about that one? Any other homework questions? Okay. Anyone remember what we were talking about last time? Centroids, yep. So back to centroids. Um, and what we finished talking about last time was how to calculate the centroid of a shape, and then that's where the weight force is applied. And where you put the weight force can affect the reaction loads. So you need to do that. You always need to know where the centroid is. If you have circular shapes or rectangular shapes, you can just look at it and tell where the middle is. The centroid is in the middle. But if you have other shapes besides that, you need to do the calculation. Okay, so now we're going to distributed loads. And really, like I said before, the weight force is a distributed load. But the idea here is we'll see things like this, where you have this cantilever beam is connected to the wall. And instead of being applied at individual points, the load is applied in terms of a function that represents how that load is spread out. This could be something like, up at this point, this would be like 10,000 newtons per meter. And one thing to keep in mind is, so notice, really all loads are distributed loads. No forces are really applied at a single point. Applying a force at a single point would be the equivalent of using an infinitely sharp knife to apply a force. It would, like, everything would go crazy. It would just cut right through the material. The stresses would be infinite at that point. All this weird stuff would happen. So really, even though we always use this idea of point forces, that's really the one that's the mathematical like invention for our ease of calculation. So all forces are spread out over some area. Even if you sharpen a knife as much as you possibly can, it's still spread out over some area. And when you look at a distributed load, it has this weird form. We haven't seen anything like that before. Notice that what it says is that at any spot along the beam, the height of this function tells you what the what the intensity of the load or the density of the load is at that point in terms of newtons per meter. Okay, we haven't seen that before. So I want to make sort of an analogy with what that means to what speed means. Okay. So let's think of, so over here, let's think of like distributed load compared to force. And analogously, on the other side of this table, let's think of instantaneous velocity compared to displacement, or let's just say distance. We don't have to be too careful about this. This is just sort of like a intuitive understanding of what's going on with distributed loads. Um, okay, so a distributed load, if you look at this load up here, okay, what's the force vector that this distributed load applies, say, at this point right here? You know, what in newtons, what force is this distributed load applying here? The answer is 0. It's an infinitesimal force. Okay. And the only way a distributed load applies a finite force is if you evaluate that distributed load over some finite distance. Okay. So uh, a distributed load only applies a force over a finite interval. At a single point, the force is infinitesimal. That seems a little wordy, but that's the best I can. I did my best. That's the theme today. Okay, but now let's make the comparison between this and how like velocity compares to the distance you travel. So say you're going 55 miles an hour. How far do you go at a single instant? You know, you don't go anywhere in a single instant. It's infinitesimal. You only travel a finite distance over some amount of time, over a time interval. Okay. Um, so it only causes finite distance traveled over a time interval. With the distributed load, we're talking about um, a length interval. Bless you. With with velocity, we're talking about a time interval. At a single instant, the distance traveled is infinitesimal. You're really used to how this works for velocity and distance and stuff. It almost seems like ridiculous to ask the question, like, how far have you gone in a single instant, you know? But we're just not used to the idea of distributed loads yet. And so I think this can sort of help you make sense out of it. This one isn't going to be as wordy. Um, I only need two here. I sort of put the second one into the first one here. So the only other one that I have is the magnitude of the distributed load of the distributed load at a point is the force that would be applied if that distributed load were constant over a whole meter. If that distributed load were a constant over a 1 meter interval. And that's the same thing that velocity or speed tells you. The magnitude of the speed at an instant is the distance you would travel if that were the constant speed for a full second. Or if you're doing in miles per hour, then it's over a full hour, you know, but it's whatever unit of time you're using. If that were the constant speed for a full second. Okay, so if you look at this picture here, how strong is this distributed load right here? Well, it says that, imagine this, the length of this cantilever being 1 meter, okay? If this were the distributed load over the whole thing, then the total force applied to this would be 10,000 newtons. And that 10,000 newtons would be spread out over the whole thing. This is going to be less than that because the highest it ever gets is 10,000. And at this end, it goes down to 0. You know, there's no distributed load at that end. So in like analogy with speed, that's sort of like if you start out at 0 speed and then accelerate to a high speed, what's the total distance traveled? You know, you start at 0 speed, accelerate to 55 miles per hour over a full hour, you're not going to have traveled 55 miles in that hour. Okay, I'm talking too much. It's but so now for calculations. So it for a distributed load, with a given geometrical shape, the total force applied is the area of the distributed load shape and second, for an equipolant system, that total force has to be applied at the centroid of that shape. Okay, so let me do an example. Let's use the example that I drew up above. So let's say we have a cantilever beam connected to the wall on the right. And let's say it has a length of 1 meter. And the distributed load has a triangular shape with a maximum value of 10,000 newtons per meter. We want to know what are the reactions at the fixed joint. And for this one, I'm going to ignore the weight of the beam. I mean, if we knew the mass of the beam, we could add that in. So we'll skip that. And that just represents a case where the weight of the beam is very small compared to the other loads applied to it, where, you know, it doesn't, you still get the level of precision you want without considering the weight. Ignore the weight of the beam. Okay, well, our distributed load shape is this. And I'm going to draw it with dimensions that we're used to, just so you can see what kind of shape it is. But it's not going to be drawn to scale at all because the forces are going to be huge and the lengths are going to be in meters. So they're going to be really small. But so what we have is a width of, or a base of 1 meter. And this is a right triangle, and we have a height of 10,000 newtons per meter. So the area of this shape is 10,000 newtons per meter times 1 meter divided by 2. That's just the area of a triangle. And so you get a total force of 5,000 newtons. Notice the units even work out. And then the centroid of that shape, remember, we know a formula for the centroid of a right triangle. And like if you always think of whichever way you lie a right triangle down, there's a wall side and a point side. Okay? Vertical side and a point side. And we're always going to go 1/3 of the way from the vertical wall side toward the point side. Okay? You can always think of that. So the centroid in the x direction is going to be 1/3 of a meter from here to here. And if we imagine flipping it over this way, it's also going to be 1/3 of 10,000 newtons per meter this way. Okay. So, and that means if I put the coordinate system like this, the x centroid is going to be negative 0.6 repeating meters. And the y centroid is going to be positive 3,333.3 repeating newtons per meter. This one we're not going to need. And why is that? Why don't we need the vertical one? That's right. So it has to do with moving the weight along its line of action. The weight's line of action is up and down, so the vertical position doesn't matter. because the line of action of the weight is vertical. Okay, so we can forget about this one. And now I can draw a free body diagram. So we have the beam. At the fixed joint over here, we have a full force vector. I'll call it R. And it's not allowed to rotate there, so we also have a couple. I'll call it MR, reaction moment. And then we have a downward force with a magnitude that's equal to 5,000 newtons. And the location is 0.3 repeating meters from there, 0.6 repeating meters from there. Any questions about that? Okay, so now we can write out the table, the row vector, force vector, moment vector. So first, I'll do the reaction force, and let's put the about point over here. So the row vector for R is 0. The force vector is Rx, Ry. Cross product is 0. And then I'll do the couple. For the couple, we don't care about this stuff. We just add on the couple in the moment column. And the last one is the 5,000 Newton force. The row vector for that's the vector from the about point to where the force is applied, is negative 0.6 repeating and 0 for y. The force is 0, negative 5,000. Let's see. And so the cross product is positive 3333.3 repeating. So Newton's second law says Rx, Ry plus 0, negative 5,000 is equal to zeros. So the R force vector at the wall is 0, positive 5,000. And the moment equation says MR plus 3333 is equal to 0. So the couple required at the wall is negative 3333. And the units for the force are newtons. For the couple are Newton meters. And notice how that 5,000 Newton force is distributed. You know, it determines where the centroid of that shape is. That affects the answer to the reactions, because if you look at that 5,000 Newton force, the moment comes from the cross product, you know, comes from a calculation involving the location of the force. So if the centroid of that shape is farther away from the about point, this is going to be bigger. If it's closer to the about point, it's going to be smaller. Um, any questions about that? Okay, let's do one where we think of weight as a distributed load. It's not going to be useful to us yet, but later on we are going to have to think of it this way. The moment. If that, so always looking for an equipolant system where we apply that force as a point force, right? We apply that distributed load as a point force. If that point force is farther away from the about point, then it's producing a bigger moment. If it's closer to the about point, it's a smaller moment. So this example is going to be weight as a distributed load. So let's think about a beam that's connected to a pin joint, connected to the ground by a pin joint at the left end, and a roller at the midpoint. And let's say that this beam has a mass of 50 kilograms. And let's say that it's 2 meters from the end to the midpoint, and then another 2 meters to the other end. Okay, well, as long as this shape is cylindrical, you know, the whole way along the length it has the same cross-sectional shape. The effect of the weight is a uniform distributed load. And so here we have a force vector, I'll call that RA, and then a upward force from the roller that I'll call RB, and then a uniform distributed load. So a distributed load where the value is the same the whole way across. And how would we calculate the magnitude of that distributed load? Anybody have any ideas? Well, it's the weight. And so that total distributed load has to come out to a force of 50 times 9.81. Okay. And then it's just going to be divided over the whole length to get the distributed load. So this is going to be 490.5 newtons divided by 4 meters, or what is it? 122.63. Thanks. Newtons per meter. Okay, so that's our first free body diagram, but we can't do anything with it mathematically until we represent that distributed load as an equipolant system. And so now we'll think of this distributed load as a shape with a height of a rectangle with a height of 122.63 and a width of 4. Okay. And that says that the area is 4 times 122.63. Well, that just gives us that 495. And the centroid of a rectangle is right in the middle. And so now I'll draw a new free body diagram, the one that we can use for calculations. And we have our beam We have our force over here of RA. We have our upward force of RB. And we have our downward force at the center of the shape with a magnitude of 490.5. And so what we've done is use the idea of a distributed load to come back to exactly the way we've treated problems all along. You can sort of see the connection between these two. Hey, this is what we always been doing. And then we could do that calculation, but it's sort of boring. Nothing too hard about that. So let's just go on to a little more complicated example. Okay, so let's say we have a pin joint over here. And a roller at the middle. And then we have a distributed load that goes from the middle to the end with a triangular shape. And at its highest point, it has a value of 2,000 newtons per meter. And let's say that the mass of the beam is 20 kilograms. And let's say this is 1 meter and this is 1 meter. What are the reactions? Well, we want to draw a free body diagram of the beam. Over on the right side, we have a force vector. I'll call that RA. In the middle, we have a roller, RB. We have a weight force acting down at the center of the beam. We could do that as a distributed load, but we just end up coming back to this. So 20 times 9.81 is 196.2. And now we have to represent that distributed load. It has a height of 2,000 and a width of base 1. The area is 2,000 times 1 divided by 2, so 1,000 newtons. And the centroid, all we care about is the x location of the centroid. Since that whole base is 1 meter, we know that this is 2/3 of a meter and this is 1/3. And so now I can apply this downward force over here. It has a magnitude of 1,000. And we know that this distance is 1/3 of a meter. So rho vector force vector moment. So first, I'll do RA. The about point I'm going to put over here again. So the row vector is 0. Force vector is RAX, RAY. And the moment is 0. Then I'll do the weight force next. The row vector to the weight force, that's in the negative x direction, a distance of 1 meter, so that's -1, 0. And the force is 0, -196.2. So the cross product is positive 196.2. By the way, sort of a shortcut for that's pretty easy to do, probably easier to do than writing out the table and doing the cross products when you have horizontal bodies like this, is just think of, since these forces are all vertical, just think about multiplying that vertical force times the horizontal distance to the about point, and then just think about whether it would make it rotate clockwise or counterclockwise. We'll talk, I mean, I'll describe this in detail later, but notice that what we have here is a force of 196.2 acting a meter away from there. So 196.2 times 1 is 196.2. And applying a force there would make it rotate around the about point counterclockwise, so it has to be positive. And then next is the force RB. RBs. That's at the same location as the weight. So the row vector is -1, 0. Just kidding, I don't like RBs. Just kidding, I do. Okay, the force, that was stupid. Force vector is RB, 0 RB. Cross product is -RB. And then the last one is the distributed load, the 1,000 Newton force. Okay, so now things get a little, I mean, it's not really complicated, but you can't just use the fact that we calculated that 1/3. You know, you have to think of the distance from here to there and then the distance from here to there and sort of put them together. So what's the distance from the about point to a point that's 1/3 of the way from the end? Well, it's 2 meters to get all the way to the end, and it's 1/3 of a meter short of that. So it's like 1 2/3 meters, 1.6 repeating meters, and that's in the negative x direction. So -1.6 repeating, and then 0 for y. And then that force vector, it has a magnitude of 1,000 in the negative y direction, so 0, -1,000. And the cross product is positive 1,666.6 repeating. Any questions about that table? Okay, so Newton's second law, RAX, RAY plus 0, -196.2 plus 0 RB plus 0, negative 1,000 is equal to zeros. And then the moment equation says 0 plus 196.2 minus RB plus 1666.6 repeating is equal to 0. So RB is, what's that? 1864.86 repeating. 1862.86 repeating. And then plug that in and you can calculate the R vector is 0 for X. And then what is it for Y? I guess 666.6 repeating. And all of that stuff depends on the location of the centroid of the distributed load. Any questions about that? Okay, well, let's stop there and I'll give you some problems to work on and I can answer questions about them on Thursday and then I'm done talking about centroids and we can move on.